first. I'm Matteo. I was, like all of you, a physics aspirant in AC1, took part in SPhO, went to the sport team, eventually went to IFO. Just came back from France about a few weeks ago, got a silver medal. So now I am going to be hosting this lesson on one of my favorite topics, EMI. So hope you all like it. And yeah, I think without further ado, I'll just start now. Some of y'all send me some questions, like 2.10, 2.12. I'll go through that later. So we'll spend about 1 hour going through content, and then an hour going through problems, taking a short break in the middle. From what I understand, or what how Yang told me, you are quite solid lah. So like, I think I'll go like a bit faster. If I go too fast, like you'll just tell me to slow down. Okay, so without further ado, I'm gonna start. So basically, what is EMI about? You all can all see my screen, right? The one on the iPad, my screen on the iPad. You can see, right?
Yeah, we can. Yeah.
Okay, solid. So what is EMI about? Okay, EMI is basically bringing time dependence into EM. Is really quite simple. So you learn before this, you learn electrostatics, you learn magnetostatics. Now we're going to see what happens when your fields change with time. So in Maxwell's equations, you see these terms, right? So we're going to deal with them and their implications. So first of all, we got to talk about EMF lah. So what is EMF, right? Basically, it is just a force per unit charge, and you integrate it. So it's called a control integral. It's basically a loop. So you integrate it about a closed loop. Okay, and F is your force per unit charge, which can be any force. So this can be electric, it can be, magnetic, electric, electrostatic, whatever, any force. dl is your infinitesimal line element. So right now, right, when you're basically given this, you may think like, okay, wow, what's the deal? What's the deal with this? It seems quite random. Um, it is quite random lah, but I'll just introduce it here and I'll show you the usefulness later. So, for example, you can use it to solve some problems already, right? Say you have a metal disc, radius L, parallel to this plane, then it rotates at omega, constant field BZ that goes through the disc, and there's like a resistor or resistance R here. So in 2D is basically this is the plane of your loop, right? And then which I just represent it as a line. And then after that, a field is points something like this, right? And then at two ends, it's connected, and there's a resistor R here. So what is the EMF between point A and point B? Well, okay lah, you just apply the formula, right? But first you need to find your F, okay? Then your F, right, which is your force per unit charge. So you start from this guy, Q equals B. Your F is just a big F over Q, which is V cross B. And now you need to find the direction of this, right? So the question gives that omega is actually counterclockwise. So your V is going to be uh, say like for example at this point it's going to be into the page. So V into and B up, and then you do your right hand rule, you find that oh it's actually pointing in this direction. Your F is pointing in this direction. And then okay lah, then you just find your F dot DL. So because you're integrating from the middle to the end, so your DL is in this direction also. So this is basically the magnitude of F and the magnitude of DL, right? Because your dot product is in the same direction. And this will be VB DL, right? And then of course you have to integrate it from this point A to this point B. Okay, technically you have to do a whole loop integral, right? But let us assume that your B field, right? Your B field, it sort of spreads out. It spreads out like this. So actually, uh, because the problem is that if your B field, right, it actually goes straight like this, then when your current flows through this portion of the circuit, there will also be contributions to F dot dl, right? Because there will be there's your current and then there's your magnetic field at perpendicular directions. So we have to assume that your magnetic field it will spread out like here lah. So there's no contribution to here that this part will deliver. So your EMF, right? So this guy is simply equivalent to the integral between A and B of this, right? Yeah, which is they wrote here lah. So you just integrate. I think this is quite straightforward for you all lah. So V equals to omega L, then integrate, and then that's your E. This is your E. And you find your E, you find your I, which is E over R. Okay, but usually you learn that like V equals to IR, right? And then why E equals to IR in this case? It's like they just threw you this equation E, this random equation, and then you say it's supposed to be IR. Why is that the case? So let's look at why it is the case lah, right? So to explain this guy further, notice that F can be electrostatic or non-electrostatic. So we split it up into these two portions. Okay. But your usual electrostatic field is conservative, which means that the curl of E equals to zero for those of you that know your vector calculus. And actually, by this formula called your Stokes theorem, if you should read if you want to learn a bit more, right? This is equivalent to the fact that contour integral of E dot dl is zero. So, uh, electro the contour integral of your any electrostatic field dot dl is going to be zero because this is basically your E, right? Okay. Um, and what I'm going to do next, right? Uh, okay, let's imagine we have a certain battery. Okay, so this is your battery. Okay, this is your positive terminal. This is your negative terminal, and I know that um how a battery works, right? Is it works by having both electrostatic fields Fe and non-electrostatic fields driving charges. Okay, so I know that my electrostatic field is will go from a positive to negative. So actually, your electrostatic field looks like this. Okay, so you imagine a positive charge plus Q, right? It will be driven here. That's how it goes from positive to negative. But within the within the battery itself, right? It will go from plus to minus. So it will actually go this opposing direction, right? So then my question is, right, say your charge from plus Q finally comes all the way around, then it reaches here. Why does it continue to go across the battery? Well, this is due to the non-electrostatic field. So actually within the battery, there's also a non-electrostatic field, FNE, right? I will color it in blue. So this non-electrostatic field that opposes the electrostatic field, okay, uh, such that the force on this charge is actually zero. So it's exactly the same strength. So what happens is that your charge will move from here, right? And it gains zero energy because zero work is done overall. And then after that, what happens? The non-electrostatic field only acts within this range. It could be like some chemical potential if you learn in your not chemical potential, sorry, some chemistry thing. It could be because of like your induced EMF also. But anyways, it's within this only, this location only. So after when it gets here, then it's driven by your electrostatic field back again. Okay, that's how a battery works. So, what we do, right, is that let's define 2 points A and B. So A I'll define here, B I'll define here, and then what we get is that your equation, because we know that this guy F electrostatic dot dl is 0, we just have to consider this. Okay. So, and because this guy only acts across A to B, I can change my contour integral to a integral from A to B. So this is your E, right? Okay, then, however, let's recall the definition of the electric potential. Your V B minus VA is actually B going to A B dot DL. Okay, so there's a small mistake here lah. Shouldn't be this. Uh, your limits of integration be vectors, and it should be from B going to A. There shouldn't be a minus sign here. So can you all change this your problem set to this? So this is the correct formula which you should learn by heart. It's very, very important. So E in this case refers to the electrostatic field. But we already know that within the battery, right, your electrostatic field equals to negative of your non-electrostatic field because this is so that it does not gain any energy. Your charge does not gain any energy, any kinetic energy, for example, when it goes through the battery. So so this guy I can minus F NE non-electrostatic dot DL from B to A. And actually what is this? So this is basically from A to B of your F NE or DL. So if you look at this guy, it's exactly the same as this guy. So hence, actually your electromotive force, EMF, equals to your potential difference in the battery. So hence, when we say V equals to IR, we can also say V equals to IR. That's the reason. Yeah. Um. Okay. I mean, but of course, when we deal with the induced EMF, right? When we deal with induced EMF, we have to take note uh that it's not something like a battery. So it the induced EMF has is basically a non-electrostatic force, right? It isn't caused by uh collections of charges. It's a non-electrostatic force, but it doesn't act. If this is your circuit, it doesn't act only on this like at this location. It acts throughout the circuit. It acts throughout the circuit, right? Because it just does lah. It acts throughout the circuit. And I'll explain this later. So this is something you take note. But either way, you can use this analogy, and you can note that actually your delta V potential difference goes to E. So the formula. So that's why we can still use this lah. Yeah. Let me move on to the next section. Okay, this is about Faraday and Lenz's law. So yeah, it's okay. It's basically just this Uh, this is your magnetic flux linkage. I won't bore you all with this. I assume you all know already. Lenz's law just basically means that it just explains the minus sign lah. Direction of induced current will be such that it opposes the change that created it. Um, this statement is a bit. I don't really agree. Um, I think a more accurate statement is the fact that if the direction of the induced current supports or strengthens the change that created it, i.e. the opposite. So basically if E was positive d psi b by dt, then this contradicts COE. I think this is a more accurate statement. I don't think you can derive COE from this lah. So can you all just cancel this? Yeah. But this is true. You can think about why it contradicts. Maybe you can think about an example if you have free time, right? There's many examples to show why it contradicts if it's the opposite. Okay. One remark here. This equation is very versatile. So it it doesn't it doesn't work for just like stationary loops. So stationary loops, of course, it works. But your loop can move, it'll still work. Your loop can even expand in size, it'll still work. So yeah, this is very important. Remember it, guys. Next, wow, all the images are not here. I think I downloaded the old version. It's okay. I'll just draw it out lah. So let's see how to apply. A rectangular metal loop with a very long length and a width h. So is partially placed the constant uniform magnetic field B pointing into the page. So suppose this is your B. And the resistor R part, let X be indicated as the figure below. So okay, I'm guessing X is this lah. Yeah. Then verify that both equations 1, which is this, and equation 6, which is this, give the same expression for the induced EMF. So, okay lah, let's see. Uh, okay, and let's say this loop is actually moving at a speed v, like that. So, let's first use equation 1. Okay, so imagine your positive charges here. They are going V, and B is into QV cross B. The force actually here. And then how about your DL? Your DL, say we integrate clockwise lah. So this is your DL. Okay. So your F dot DL is just EB DL. Okay. All right. And here here there is like, because your DL is here and then your F is here, so there's no contribution. For this, your DL is here, F is here, no contribution. Here, there's not even a B field, so there's no F in the first place. That's why we limit it to from A to B. Yeah, and if I integrate, then okay lah. So we get dv, and then your integral of dl is just h. Everything is constant, so you get this. Okay, let's now use this guy. So first you find psi b. Okay. Now, because you know that you already chosen a direction to integrate around. So actually, this direction, so I'm saying I integrate in the clockwise direction. So let's note that when we choose a direction, it's actually very important. Okay, because in EMI, your direction, your area vector, whatnot, is very important to not make sign mistakes. So if I'm integrating around clockwise, right, I must use my right hand grip rule. My right hand grip rule will tell me that my thumb will point. You all try. So you find that your thumb will point into the page. So your thumb will point into the page. And actually, this is the positive direction or area for your area vector. Okay, and what's your area vector? Your area vector is what you use to compute your psi b lah. Because you know your psi b is actually b times a, right? Then your okay, it's actually this lah. It's actually your b dot dA. Yeah, yeah. So it's actually this, your b dot dA. Okay. And in this case, your dA will point downwards. Okay. and your B will point downwards also because it's into the page. So this is positive. It's positive B multiplied by what's your A? Your A is this lah, so it's your Ajax. Then your d psi B by dt, just BH dx dt. And your dx by dt is, oh, sorry. Yeah, that's correct. And your dx by dt is minus b. Why? Because your v is positive, but your x, which is the distance between the edge of the loop and the magnetic field, you can see that your x will decrease lah. Because after a while, your loop will be like this, and then there's less. This is your new x, so the x decrease. There's less x. So dx dt is negative. So this is minus dh3. And then your e is minus d psi b by dt, which is positive dh3. So actually, your induced EMF is bhv. Induced EMF bhv. They tally. Physics works. No problem here. Uh, but I think a good practice is always to write your E equals to bhv in the clockwise direction. So you know which way your E is going. So in this, maybe I emphasize again the point about direction. If if you chose if you wanted to choose the anti-clockwise direction, that's also okay. Just that this would be your DL, and your F would still remain your F. So actually, your E would then be negative bhv. So it will be negative bhv in the anti-clockwise direction, which is the same as positive bhv in the clockwise direction. Okay. So physics always works. It's just the direction and the sign convention you have to get right in this case lah. And then one more thing. If you integrate like that, then your area vector, you use your right hand grip rule. It actually points upwards. So then in this, when you're calculating this guy, you have an extra negative sign. So but it still tallies with this because you just times -1 on both sides. So yeah. Uh what's part I? What's the direction of the induced current? Um it will oppose the change that causes it. Okay, I think quite straightforward. I'm gonna skip this part. Okay, next part. Induced electric fields. Okay, so let's consider moving a magnet into a circle. Okay, there's no image here. I am I'm assuming it's like the same circuit as before. Just that if this is your magnet, and then I want to move it slowly, slowly, slowly to here. Then you find that as the magnet enters the circuit, your d psi b by dt is non-zero, hence your E, which is the negative of the latter, is non-zero. Which means that this guy is non-zero lah. So there's definitely a force per unit charge. But what is the force? Because I mean there's no electrostatic field. So what is the force? So the answer is the induced electric field. So there is no electrostatic field, but there is a induced electric field. Okay. So meaning because your electric field, right? How you can produce it? I mean, one way is you use charges, but the other way is so charges is your electrostatic field. But your other way is through changes in psi b. Okay, and this is your induced electric field. Okay, this is very very different from your electrostatic field. It's still a force per unit charge, but the curl is non-zero. Okay, and it's not produced by charges. Yeah, so it basically is your Faraday's law lah. So we know that Maxwell's equation, right, this is this. If you all see. So this is the differential form, this is the integral form. And your E in this case, right, in the Maxwell equation, it represents both the E induced plus your E electrostatic. But the closed loop integral of your E electrostatic is zero because it's conservative. So actually, this is as good as this lah. Yeah. So now let's compare this guy with this guy. So remember, this is our definition of the EMF. And then you'll see that because I talked about how E equals to minus d psi d by dt before. But then your Faraday's law also has E dot dl equals to d psi d by dt. So this is what we learned already. This is Maxwell's equation. So let's compare both sides. And you see that, oh, this guy is the same as this guy. So actually, your F in this case is just your E induced. Yeah. Uh, yeah, I went through this already. Induced electric fields are non-conservative. So, like, still remember earlier in the battery, they're going to be conservative lah, because your your closed loop integral is zero, right? So you integrate around a loop. Here is dl, and then here is your E. So here E dot dl is positive. But then when you reach within the battery, I don't care about the non-electrostatic field. I'm just looking at the electrostatic field. Here your E is like that, and then your dl is like that. Actually, your E dot dl is negative. And then actually, your positive and your negative contribution will all add up, such that your E dot dl will be zero around the whole contour. That's a characteristic of your electrostatic field. But in this case, it's non-conservative. Why? Because your electric field will look something like this. First of all, direction. Say my magnet is coming this way. So actually my electric flux psi B is going to be increasing if I take the positive direction to be downwards. Then how about my E? My E will be opposite direction to the IB. It will oppose the change in magnetic flux. So basically the E will be such that there's a magnetic field coming upwards, right? Then you use your right hand grip rule, you'll find that your E is actually like that. So this is your induced electric field. And the thing is that you note if you integrate, you do a loop integral around this loop, your E dot dl positive, E dot dl positive, E dot dl positive, E dot dl positive over all your E induced, or dl is positive. Okay, so it is non-conservative. Yeah, very important to differentiate these two. Induced electric field and electrostatic field. Okay. Now let's talk about more complex situations. Yeah, so this is from Griffiths. Y'all can look at it if you want. So you have a line charge lambda glued to the rim of a wheel of a radius d, and it's suspended horizontally such that it is free to rotate. Your spokes are non-conducting. Basically, just ignore the spokes. In the central region, there is a uniform magnetic field B naught pointing upwards. And then someone turns this field off. What happens to the loop? Okay, wow. Pretty complicated, right? But like let's try to break it down. Alright. Um okay, fine. So y'all can think about this for a while. Take a sip of water. Okay, so what happens? Uh, Basically, your B naught turn off, right? So your B basically decreases lah. There's a change in magnetic flux. Hence, there's some induced EMF. Okay, this induced EMF will cause a potential difference. It kind of is the potential difference lah. So, what happens is that, right, there will be a torque. There will be a torque that's acting, right? Because your EMF is a force per unit charge, right? So, this is basically your E induced. It's a force per unit charge, and this will cause a torque that will rotate. That will rotate your thing, right? Your wheel. Okay. So, let's calculate lah. Let's calculate it. Okay. So first of all, I think maybe a good idea is to find what is the E around this wheel first. Okay. So I know that my E, right, is either E electrostatic or my E induced. Okay. What's the E electrostatic? It's actually zero. There's no charges in this. No, no, sorry. Okay, there's charges, but due to symmetry, because it is all symmetric, right? It'll be zero. Okay. So now your E is really only your E induced. Okay. So Faraday's law tells me this is what is d psi b over dt, right? Uh, uh, so first of all, let's get the direction here first. Let's say positive direction, we define it to be like upwards, like in the arrows here, right? Then your B decreases. So your your induced electric field will be such that it will push the charges to produce a magnetic field that will increase the magnetic flux. So be clockwise. Okay. And then so say then because you define your positive direction to be upwards, your DL you have to integrate around like clock counter counterclockwise. Yeah. So your E induced dot DL will be positive. So this will be E induced times 2 pi B, right? Because of symmetry, I assume my E induced is the same strength everywhere. And equals to d psi B by dt. So this will be d by dt. And what is the psi B? The psi B is basically your B naught multiplied by pi squared. First equation. Then my second equation, um, okay, maybe what do they want to find? Okay, they want to find angular momentum. I want to find angular momentum imparted to the wheel. Okay, so uh, what's my angular momentum? It's actually because my tau equals to dl by dt. I don't know if you all went through this before. I think you all did. But anyways, you all should know lah. So because my tau equals to dl by dt, right? My L is going to be the integral of tau and dt. And I know that my angular, like the thing will rotate counterclockwise. That's confirmed. Because my E points at that, and then my charge is positive somehow, right? So I don't have to care about signs, right, already. So then now I just need to find my torque. Okay. So my torque is what? My torque is just your R cross F lah. But again, we don't care about signs. So it will be B multiplied by the total force. What's the total force? Well, because each this is a uniformly charged distribution, right? And then everything is symmetric, right? So I can just write that my total force equals to, well, it's just E induced times U lah, which is the total charge. So uh uh, maybe I let me reiterate. So technically you're supposed to integrate all your tiny top elements. But I'm saying because the force on each tiny element is the same and the distance to the center is the same also. By symmetry, I can just skip this integration step and I'll go straight to this. Make sure you all understand this. Okay. Um, so I will just simplify P induced. And then Q is what? It's just your lambda times L, which is 2 pi b. Okay. And now we're ready to put everything together already. L equals to 2 pi b squared lambda E induced is d dt, no, pi e squared, 2 pi b dt. Um, so yeah, simplify. And this becomes lambda b naught pi a squared. Is it correct? Yeah, it's correct. Um, one one small thing is an integration pet peeve. When you have this the correct way of doing this is to say from 0 to tau and basically at tau your b is 0 and at 0 your b is b naught. I just want to write the step clearer. So this will be is actually d naught pi a squared. Uh, from okay, I want to make this very clear. Here, what 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 should this this limit be, right? So the bottom limit actually should be e naught pi a squared at t equals to 0. And your top guy would be e naught pi a squared at t equals to tau. Okay, so this is not, your bottom limits are not 0 to tau anymore. Okay, because your differential is this guy. This guy is your differential. Let me repeat. Okay, this is very important in physics because I've seen like a lot of people, like even sport people, they get like careless because of this. So let me repeat that these should be your limits. Okay. Obviously you don't need to write, so you don't need to write so like so nice when you're doing an exam, but just take note so you don't make careless. So when t equals to 0, um your b equals to b naught lah. So it's actually this is b naught I squared. When t equals to tau, b naught, your b is 0. Oh, sorry, this should be b, not b naught. This should be b. Yeah, your b is 0 and t equals to tau, so this is 0. Okay, so this is minus b naught I squared. But I already told you that like I don't really care about the signs anymore because I already know the thing will rotate clockwise, so I can just get rid of the sign. Yeah. Anyways, this is correct. So yeah. Okay, is everything like good so far? Like how's it going, guys? Uh, maybe Austin, is everything going good?
Yeah, it's going well.
Yeah, okay. Like too fast or too slow or anything?
I think I'm following fine.
Following. How about Jaden? Doing good.
Yeah, it's okay.
Okay, too slow for you. I can go faster. Okay, okay, never mind. Yeah. Wait, okay, I'll just continue. Yeah, I'll go a bit faster lah, cause uh maybe 20 more minutes. So inductance. The whole principle behind inductance, right, is that like if I change the current in the loop, right, my my magnetic field that passes through the loop will also change. Hence, my magnetic flux will change. Hence, there's a EMF induces the EMF in the loop. So inductance is just how you quantify this. So let's look at the Biot-Savart law at first. And you see that B is actually proportional to I. So for a loop of constant area, because your psi B is B dot dA, if your area is constant, then your psi B will also scale with B. So actually, and then because your E, right, is negative d psi B by dt, so your E will actually be proportional to di by dt. So we just call L as the constant of proportionality. Okay. Um, but like, what's a simple formula for L? Well, let me compare with this Faraday's law. So from here, you can read off that psi B equals to L times I. L equals to psi B over I. So, like, it's not complicated a lot. Like inductance is basically it just literally means you have a random loop, and then if you run a current I, what's the psi B that goes through it? And the answer is the inductance law. So that's literally what it means. It's not complicated, guys. Um, yeah, it's a purely geometric property. Doesn't depend on current, right? Because it's just a proportionality constant. Depend on quantity, yeah, sure. Usually refers to self-inductance. Yeah, it's quite straightforward lah, right? Long solenoid of n turns, radius r, length l, current I, right? And I mean, your can just derive, right? This is your okay. The only thing is like you know that when it's n turns, your psi b you have to multiply with n r. Then the rest is straightforward. So for a is just I r squared. Then your b is just mu naught times the turns per length, which is n over l multiplied by I divided by I. And you get n squared pi r squared mu naught over l. Yeah, you can tell it's depends on the geometric properties only, so doesn't depend on current. Next, I'll talk about energy. This is quite important, because like sometimes they'll ask you they'll like in an Olympic question they'll ask you like many topics. One of the questions they'll bring in like energy conservation. Then you have to answer using energy conservation, and there's EMI involved. Then the this section is actually quite important. We talk about energy in inductors. So uh okay, before I go through the formula, let's look at let's look at like a circuit. Say you have an inductor here, and then you have some current flowing, right? So I know that my I know that say this will create like a EMF, this inductor. So this is the EMF. Sorry, what am I saying? It will create a magnetic flux through the inductor. So say this is psi B that's created by your current I. But then I already tell you that by this Faraday's law, there'll be an EMF induced due to the changing magnetic flux. So say your current goes from 0 to I lah. So there will be an EMF induced and it will oppose this magnetic flux. So this is your opposing ID due to your EMF induced, which we call it a back EMF. Okay. So yeah lah, yeah. So this is your opposing side B. So this now you look at this current and why is it called a back EMF, right? It's because to drive the current through, right? Well, you need some battery. Okay, let me use E naught. This battery will drive the current through. Okay, so this is your like your normal EMF, right? But then your this guy, your inductor, will try to create opposing side B, and it will induce this back EMF E, which is minus L E I by dt. Okay, to try to oppose your current. If you think about it, right? If you think about it, what is the energy? No, let's not talk about energy. Let's talk about okay, what's the power needed to drive some charge dq through this circuit? through this guy. Well, okay. So I will need to oppose my back EMF E, right? So your P goes to the I. But then to oppose your back EMF E, right? You actually need to put in minus E, right? Multiply by I. Then because your E is negative L di by dt, so this will be L di by dt I. Respect to time, to get energy, just get half Li squared. So that's your energy stored in an inductor. Let me clarify one more thing. So there'll be a back EMF E, right? So it basically works like another battery, like an opposing battery. So for example, this is your circuit. This is your this is your so-called front EMF. It's just like I don't know, you put in a battery or something. Then there'll be a back EMF that will oppose. So uh so at any time, right, your effective EMF is basically E naught minus E. So that's what the inductor does in the circuit. Okay, so we can generalize this to volumes of space. Um, like you can basically you do this through like vector calculus. Griffiths has a chapter on it. You can read it if you're interested. But anyways, you can generalize this concept with the magnetic energy density. So this is basically the energy stored in the magnetic field. So basically, if say originally there's like empty space, and then now okay, empty space and like a circular loop. Okay, then now I run a current through the circular loop I, and then it generates like a magnetic field B around it. How much energy is needed, right? I can basically find E squared over 2 mu naught, and then I integrate it dV. I integrate it over all space. That is the energy. That's the total energy you need to overcome the self-inductance of this loop and change your current flowing through this loop from 0 to I to fight against the back EMF. So uh so you can use both like half Li squared or this guy. It's just an alternative, right? Okay. Uh Verify the energy stored. Okay, so basically I just verify the energy in this solenoid. Okay, I think it's quite straightforward. I think you all can just like do this at home. So it's just half Li squared lah, and then your dV in this case integrating over the solenoid, right? And your B is constant, and then your dV is just what? It's just your pi r square L law. Then multiply, and then you'll find that it's the same. No surprise, physics works. Okay. Then you can also think uh, why because your magnetic field is like that, right? So when we are doing this integral over all space, oh yeah, let me reiterate. This must be over all space. It cannot be over like some segments of space. It must, when you're using this integral, die must be over all space. Because you can look at the vector calculus proof, you have to use all space. Yeah. So, but the thing is that when we use all space, right, there's some B that's like outside the solenoid also, right? So there will also be a contribution outside the solenoid. So why do we neglect this? Answer is that the straightforward answer is that uh, is the B is like small. So my B is not. It's some orders of magnitude smaller than inside the solenoid. And when you square it, it it sort of it amplifies the orders of magnitude. So even though okay, but here's the thing lah. Um, your dV when you when you look at like outside the solenoid, right? So this is solenoid, this is outside. The thing is that outside the solenoid, right, your B decreases, right? But then the sort of total volume that you integrate over, this actually increases. So my point is that can you think of an argument that shows why B squared dV inside is much, much greater than B squared dV outside, such that you can neglect this. This is your homework. Okay, think of a dimensional, like think of an order of magnitude thing. Because we have two conflicting terms. Yeah. Number two, why do we not consider the magnetic field at the end of the solenoid is half of that at the center? I think you all know why, right? This is like the magnetic field here is like not Ni over. Once again, it's an order of magnitude argument. So you can go home and think about it. Yeah. Uh okay. Yeah. Yeah. Next, mutual inductance. Okay, this one's the fun part. Sometimes you have two coils, and in this case, you have to consider mutual inductance. So what's the idea? Let's call this 1, let's call this 2. I run a current I1 through 1. It goes from 0 to I1. Then there's some magnetic flux passing. So there's some magnetic flux that pass through psi 2, that pass through number 2, and this guy will increase. Hence, the EMF E2 will be induced in coil 2. Because uh, because your psi V2, your magnetic flux through number 2, this guy is proportional to B2, is proportional to B2, which is the magnetic field that passes through 2. But this guy by Biot-Savart is actually proportional to I1. Okay. Hence, actually, your E2, which is minus d psi B2 over dt, this guy will also be proportional to di1. What's the proportionality factor? It's the mutual inductance law, call it M21. Similarly, E1, you flip, you say like, okay, there's so now this guy will have I2, 0 to I2. This will also induce some EMF here, E1. So the same, E1 equals to M12 EI2 by dt. Okay. What is the magnitude of the mutual inductance? How do you get this? Well, once again I just compare it with this psi E2, the dt. This Faraday's law. So it tells me that M21 I1 equals to I2. Yeah. Okay, I think I messed up whether it's like M21 or M12. But like it doesn't really matter because there's a certain formula that says M12 equals to M21. So the mutual inductance is actually the same. Okay, that's a really nice there's a really, really nice proof in Griffiths. You can read it if you want. It involves the magnetic vector potential A, right? It's the one such that the curl of your B field. Sorry, no, the curl of A, right, equals to B. And then there's like a formula for this, and then like yeah, it's quite cool lah. Y'all can read. Then you can actually get a formula of M. It's like something like this. Uh, DL1 or DL2 over something, and then it's 1 and 2. But then this is called the Newman formula. But then my point is that if you see, right, if I interchange 1 and 2, if I make this 2 and 1, then I'll make this 2 and 1. The formula remains the same. So M21 equals to M12 equals to M. Yeah. So okay, but what does it show like physically lah? Physically, it means that okay, it means that I if I if I change current, right? Say I1 through this guy, and I change I1, then there'll be an EMF induced. How big is this EMF induced in the other loop? Well, it's just given by the mutual inductance. Yeah. Uh, But then, so that is what this formula means. Then you can also use this formula, the flux one, which means basically if you run a current I1 through one loop, what is the flux through the other loop? So it's just given by the mutual inductance. So yeah. Okay, let's look at this. 1.7. Uh, so they just ask you for the mutual inductance of this configuration. So you know there's two methods to solve this because your M12 is M21. So one way, right, is you say psi of let's call this big one 2, and let's call the small one solenoid 1. One is you can say that psi B2 equals to M multiplied by I1, and psi B1 equals to M I2. So both of these formulas work. But which one should we use? So the answer is that let's evaluate. Okay. Imagine I run a current I1 through solenoid 1. Then this will be my field. Right? How do I calculate IB2? Is it easy to calculate? Answer is like no lah, because there is so many guys, so many magnetic field line escaping here. Like I think you calculate that you can get like a like a master's in math, right? Math will be so ridiculously complicated. Okay. So this is not the best way. Now let's consider the second one. I run the current I2 to the big guy. What's the magnetic flux through the small guy? Oh, in this case, it's a lot easier because the small guy is so small that all your magnetic field lines are constant, so it's really easy to calculate. Yeah. So let's do it lah, right? IB1 equals to um number of turns, and this guy has what? N1 turns per unit length, and this guy has N2 turns per unit length. Okay, so IB1 is N1 times D times A1. And N1 is well the number of turns per unit length multiplied by L. B is mu naught N2 uh, I2 A1 I R is it R? Is it right? Oh A sorry. I A squared. Okay. Then this equals to M I2 for M equals to this mu naught I A square N1 and 2L. Nice. Okay, next. Oh my goodness. I'm a bit late. Okay, superconductors. Um basically just know that like it is basically a conductor that is cooled down to a very low temperature. Okay. For most materials, um the temperature at which it switches to a superconductor is called the Curie temperature. So your T must be below Tc for it to exhibit superconductivity. So what's the implications? One, rho, which is your resistivity, is 0, so there can be no electric field inside here. Also, B equals to 0. B equals to 0 in the superconductor. Yeah. Okay, I'll skip 1.8, but 1.9 is nice, wait, because there's a backstory behind it. So like maybe I introduced the problem setter. It's called Phil Kaiwen. So he's our IPHO Go, and he sent me this problem on the flight to France where I was still learning about superconductors because like I didn't know very much about superconductors before then. So he was sending me this problem, and then I thought about it. I couldn't solve it until he gave me this hint. So I'm putting it here also. Only with the hint I could solve. But anyways, like let's okay, let's do it. Let's do it. So the idea is that we have a long solenoid with n turns, radius r, length l, and there's a inductance ls lah of the solenoid. Then we have a tiny superconducting ring of radius R is much smaller than R, and there's a certain self-inductance LR is brought in from infinity all the way to the center of the solenoid. And because of this, your self-inductance of your big solenoid is going to change. So first of all, find the mutual inductance of the setup. So I think I think I is quite straightforward, right? So we have two options. One is that we calculate the flux through the solenoid over the ring, or the ring over the solenoid, right? Uh, this one is easier because your solenoid is bigger, right? So yeah, I mean straightforward. The flux through the ring, uh, meaning like when we have a current through the solenoid, this is IS. And what's the flux? What's the flux through the ring caused by the current? So it's just the B multiplied by the area. There's an N is just one because it's just a single ring over I solenoid. And this is mu naught times turns per length times current pi r squared. You get this. Then okay, now we need to talk about why the mutual inductance of the setup change. Okay. So so here's the thing about superconductor lah. You must remember the most important thing, okay? Like I thought about all these properties, but the most important one is like magnetic flux. Magnetic flux through a superconductor is conserved. If this is your superconductor, then like it can be a ring or it can be like a solid or whatever, I don't care. But the magnetic flux must be constant. Why must it be constant? Jaden, why must it be constant?
Because there's like no magnetic field inside.
No. There's a like the fundamentals. Like that's not the most basic reason.
Information.
What? Sorry?
There's no EMF.
Yeah, that's exactly right. Because the thing is that when this guy changed, right, you have your EMF, and then I already told you that your resistivity is zero. So actually, any non-zero EMF will drive an infinite current, and that doesn't make sense. So as there has to be no EMF, your psi p has to be constant. Your magnetic flux through a superconductor is conserved. Yeah. Uh, okay, cool. Uh, so So now let's understand why the self-inductance of the solenoid changes. I'll just work like this. So originally the flux through this guy, because it's at infinity, so the flux through this guy is zero. And let's look at when it's brought into the solenoid. So say now it's brought into the solenoid. Your solenoid, the solenoid has a magnetic flux like that. So this is psi solenoid. This superconducting ring, it will it will it will cause a current within it. It will cause a finite current within it that will oppose this magnetic flux. So maybe there'll be a so-called back flux. The current is this direction. So this is the magnetic flux by the superconductor, such that psi of the solenoid equals to psi of the superconductor. The total magnetic flux through the superconducting ring will still be zero. It's conserved. Okay. So and then then why does the self-inductance change? The reason is that because say my B, control this better a bit. Uh, this is say I1. So this is my B solenoid. Then my current of this guy will oppose. So there'll be some back flux, so called. And then some of this flux will escape through these rings. Some of these flux will come here. Um, then overall, right? Overall, the flux through this big solenoid will actually decrease, right? So, and then if you look at your inductance, which is the ratio of your flux over the current put in, because my flux will decrease, with a constant current I1, my self-inductance will also decrease. That's why there's a delta Ls. Yeah. But the thing is like, it's very hard to compute how much the flux decreases because like there's some this guy is so tiny, right? That there's some like that will escape like that. There's some that will escape here, here, here. There's some that will go all the way through. So calculating is a pain. And that's why we have the mutual inductance to help us out. Right? Because why? Um because right, we know that what the mutual inductance tells us that if there's an I through my short ring, it'll tell me how much flux that will actually be come through the solenoid. And it's given by delta psi solenoid equals to mi. So this is your back flux, so-called back flux. This is not a formal word, it's just a word I use that opposes uh, the original flux. And what's your new LS? Your new LS is just your new flux through the solenoid, which is your O1 minus the change. So now delta LS over LS is your new minus O over O, which is this, and then which is what it's not the first order. Wait sorry, this is not the first. Yeah, it's just it's not the first order. This is exact. This is exact. Yeah. Okay. And then after simplification you get this, right? Minus delta psi over psi. And then you use your delta psi equals to the mutual inductance times the current in the small ring, which I call it small I. But here's the thing. How do you find the current in the small ring? Well, that's why they give me the self-inductance of the small ring. Because your self-inductance is the flux through the small ring over the current. And then you can solve for the current through that. The flux through the ring divided by your self-inductance. So what is the flux through the ring? Let me emphasize this flux through the ring is due to the solenoid. So like like the ring itself will produce current to oppose the flux to always make the magnetic flux zero. Uh, but but this psi ring is what's originally through the superconducting ring. Meaning if we neglect the induced current of the superconducting ring, what is the flux, right? Uh, yeah. So then you just sub in the quantities, right? So M equals to this. I ring equals to B solenoid because the ring is inside the solenoid, multiplied by pi r squared, which is the area of the ring, and divided by Lr. Your psi solenoid equals to B solenoid, multiplied by number of turns of pi r squared. You simplify everything, you get this. Wow, quite complicated. Yeah, so I think this is like this is like I think it's a UFO problem or something. But anyways, if you can understand 1.9, it's like it's at the level of like one of the hardest, hard IPHO, very hard IPHO problem already. If you can understand this, you basically mastered this whole topic already lah. Yeah. Next, eddy currents. It's not very important. I wouldn't talk about that. Yeah. Okay, we would reach the end. Um, First of all, anyone has any questions about like the content before we go along to the questions proper? Oh, sorry. Someone asked me. Someone asked me through Discord. Um, why is there? Oh, wait. You want me to explain? First of all, you want me to explain why the superconductor thing again? Let me re-emphasize. E equals to minus d psi b by dt. Okay. Uh, so and I also have the two equations that are needed is this and also your uh what is it? I think if you have force per unit charge, this will create a current density, and then your constant of proportionality is so G equals to sigma E, so E equals to rho J. Yeah, so this should be F. Yeah, okay, so this is your second equation. F is your force per unit charge, then uh J is your no, sorry, it should be it should be this up. This one is in Griffiths. Oh, never mind. You say okay, never mind. Okay, I think the guy understood, but let me just repeat. Um, J equals to rho F for conductors. So F is your force per charge. So if there's a force per charge, it will cause a current density, okay, J, which is your current per unit area, and the constant of proportionality is sigma. So which is your conductivity. So for superconductor, this guy is infinite, meaning that if your F is non-zero, right, then your J will be infinite, and you have infinite current. So this cannot be the case. Hence, my F must be zero. If my F is zero, then my E must be zero. So this must be zero because my E is basically like the integral of the force per unit charge. And if this is zero, this must be constant. No? Yeah. Then you ask like, why is there a change in the flux of superconductor? Do you need me to explain that? Like the total magnetic flux still zero. Like you get it's just that um because originally right originally when it's very far away from the solenoid, the magnetic flux through the superconducting ring is zero. But when I move it but when I move it inside, right, like there will be some flux through it. But then the thing is like uh the superconducting ring itself will produce a current to oppose this magnetic flux such that no. Wait, so this superconducting ring is at infinity away. Is at infinity away first. So the original magnetic flux is zero. And by the law of superconductor, it states that no matter where I move this, right, the final magnetic flux through this always has to be zero. And the final magnetic flux through this equals to psi solenoid plus psi ring. This has to be zero. So this is the flux caused by the solenoid, which of course we can calculate. This is the flux caused by the ring, the so-called back flux, which we can also calculate as Ls, which is Lr, the self-inductance of the ring, multiplied by I, which is the induced current in the ring. Yeah, hopefully that answers your question. Is there any more? You can just like voice out. Yeah. It's not gonna take like a 2 minute break. Then I'll go answer some. I'll go like live solve some problems. Some I some I look through a bit. Hopefully I can solve. Or if not, it's like a bit loose aura. Okay. So I'll start at 9:18. Yeah. Okay. Yeah, I'll go through some problems. So like I got 2.10 EMI, I got 2.12, I got 2.14. Anyone wants anything else? Because these are all pretty hard. So like, does anyone want me to go through some like easier problems first, or we can just go through these? Um, 10 seconds for any call. 10, 9, 8. Oh, okay, I got some. 2.6, 2.9. Any more? Just shout out Discord anywhere. Hopefully voice, then I can hear. 2.6, 2.9. Wait, can 2.6 it is. Okay, so self-inductance of a toroid. The toroid has a major radius r, minor radius small r. So I mean, this guy is small r. ID1 enters a wire. R is much greater than R. The magnetic field is same. So it's basically saying that okay, this guy is the same. And the B is constant to it. Uh, it's the same as the magnetic field of a solenoid that's been bent into a large circle of radius R. So it's saying that the B here is equal to the same as a solenoid that's been. Oh, okay, sure. Yeah. It's just saying it's solenoid that's bent. Yeah. And show that the self-inductance is this. Basically find it lah. So first of all, L equals to psi B over I. So the first step is to find your psi B lah. So this is just the number of turns multiplied by B multiplied by area A, right? What's the number of turns? Number of turns is just N. Now the only difficult thing is when you find B. So B is mu naught times turns per length and multiplied by I. Now what's your turns per length? Well, uh, your your well, N is basically the number of turns over what length should you use? Technically you should use pi r lah, which is the perimeter. Because if you sort of imagine like unwinding this toroid, then you get a really long solenoid, and this has length 2 pi r and N turns. Right. Yeah. The reason why you can use this is also because your r is much greater than r. Yeah. If not, it's more complicated already. Anyways, oh, I got a message. Okay. It's okay. I'll get to that. I'll get to that. Yeah. So the person asked me like for part B lah, which I'll do also. Anyways, so it's n square 2 pi multiplied by a then times I lah. But then I'll divide by I by myself inductance. So this is L. So alpha is 2. Uh, A is what is what 1 over 2 pi. Yeah. Next, original toroid is replaced by one with a rectangular cross section. This one's harder. The cross section is a rectangle of length b minus a and breadth h. And show that this new inductance. First of all, when you have lawn, you must already think like how you get this lawn. So uh usually is you get it by this. So you should know that there should be something about this already. Right. Okay, let's go. So first I want to find the magnetic flux. Okay. Um and you know that because your your this this is your magnetic field is here, and then your magnetic field based on the radius will now change, right? Uh, yeah. So how do we find the magnetic field? This we have to use your Ampere's law, right? So E dot dl equals to mu naught multiplied by I, right? So uh your B, we think, yeah, okay, can. Because, for your solenoid, right? It's it's something like this. And then you can imagine it as sort of like how you find the B of a solenoid is that you have to use like your ampere loop like this. And then it's because you're cutting across a lot of tiny current sheets, right? So in this case, for your toroid, right, your B, imagine it's something like this, right? That's your surface, right? Then yeah. So imagine your ambient surface is at a radius r, and then it's like cutting across like that. I don't know if you can visualize it or not, but then it'll be b multiplied by 2 pi r equals to mu naught multiplied by the of guys number of like of wires that penetrate it multiplied by I, the current in each wire. So this is your B. Yeah. Wow, this is a really bad drawing. Let me let me uh so this is your toroid, right? I'll draw a view from both sides. So your this is your current loop. This is your loop, ampere loop you should draw. And then the ampere loop it goes up. So it's like a 3D loop. I don't know if you can visualize or not. So it's like uh it will penetrate like that and then it'll go up. So it's like imagine your ruler, your long ruler, and then you curve it such that it folds back onto itself. So that should be the loop you can use. Yeah, that you should use. My drawing is really bad. Oh, I'm very sorry. Okay, anyways, yeah, after you have this, then you can find your side B already lah. Right. So your side B is just B dA integral. So 1 over R, then your dA. What's your dA? Your dA is basically your what? Your dx dy lah, right? So I double integrate with the dx dy, where this is x and this is y, right? Then you know that uh oh sorry, this should be dr, right? So say this is your r coordinate, so this is dr. Then okay, because your b only depends on r, so when you integrate dy, you just get h, not an I. Right? H. So you're left with 1 over r, yeah. And your r goes from A to B. So this is ln D over A. Right? And now you can find your inductance, which is your oh sorry, this is not your full thing because you still need to multiply it by a factor of n. Right? So the n squared. Because there's n loops. Then your L should be 1 over 2 pi mu naught n squared h ln D over A. Okay. Eh? I got R. Oh yeah, sorry. No, no, no. Give me a moment. Where did I mess up? Uh, this should be correct. Oh, wait, sorry. I didn't. Someone send me a message on Discord. Oh, R is included in A. Oh, okay, okay. Okay, no, then I didn't mess up. Okay, okay. So B is 2, and then your 1 over 2 pi that's okay. So right. No, sorry. Sorry. K prime over R equals to 1 over 2 pi. So K prime equals to 2 pi. Equals to R over 2 pi. Yeah, okay, sure. Yeah, I checked the official solutions. Apparently it's like that. Yeah, so I didn't mess up. Okay, it's just this. Okay, next. What do you have? 2.9. Okay, let's see. Consider, wow. Consider a rectangular loop of wire, dimensions A by B. The long side of the rectangle is parallel to another long straight wire carrying current I naught at a distance L away from the closest edge of the rectangle. So there's a resistance of the loop which is R. You have to neglect self-inductance. Wow, okay. Determine the momentum P when the current is switched off. Okay. First of all, I naught will have B lah, right? So uh B of R, which is mu naught I over 2 pi R, and this guy will be actually pointing out the page. So I know that what's going to happen is that when my I drops from I naught to 0, what happens to my magnetic flux through this loop? So my magnetic flux through the loop will essentially drop from some original value all the way to 0, right? And then this will induce the EMF in the loop, right, which will induce a current, and then the current uh, will induce yeah, and then your current uh what happens to the current? How do you get this this momentum? Uh because when your current is flowing, so first we have to decide what way the current is flowing. So because your B goes from some positive value that's pointing out to 0, this guy, the induced EMF will be such that the induced flux will be pointing out, right? So it will be like this. So let's look at what happens. So now my charges of this is my current, I prime induced. Uh, QV cross B, like that. QV cross B pointing out, like that. QV cross B, like that. QV cross B, like that. So these guys they are because of symmetry, the forces will be the same, cancel. But here, right, because my B is stronger, there's a net force here, right? Is stronger than here. So yeah, then now we just have to integrate. Okay, let's see. What's T? T is FDT. Okay, so this will be F up minus F down dt. How was F? F is BIL. Is B multiplied by, so R can be either L or L plus A, right? So this is B multiplied by I, right? Which is your E over then multiplied by your L, right? And your L is A, right? And then your E is what? Your E is d psi d by dt. So okay, let's simplify. So it's mu naught over 2 pi r. And what's your F out? Your F out is I E over your R is going to be L, right? And then the A is here. What's your F down? I over L plus A, right? Uh, Something's wrong. Like, this is B. Oh, sorry, this should be B. Yeah, this should be B. Right, and then dt. Okay. Now E is d psi B by dt. So uh, this we have to be careful here, right? Because this I refers to the current in the wire. This is in the wire. Okay. And then there's also um this I is the current in this loop, which is given by E over R. So we must differentiate. So um I'll just write I wire so we are more careful. Okay, and then E. Multiplied by E, which is E psi. Again, I don't really care about sign convention now. E psi D by dt. Right. Oh my goodness. Wow. That is very tedious. So we need to find the psi b first, right? Okay, and to find your psi b, we have to integrate. Oh goodness. Okay, so I'm going to find uh b. This is my b, and then dA, right? So then what's my dA? How do I split it up? I will say that it is going to be b times dr, right? This b is the thickness of your loop, and then dr is the change in the width. So uh, where I is a know that I is a function of time. Okay. So this is mu naught b over 2 pi I ln L plus A over L. So okay. Is there any way we can simplify? Because this guy is a function of time also. Let's see. I feel there's a really nice way of writing it. Okay, sure. Let's first put everything in here first. So I'll get no b over 2 pi r. See. Then I'll move the constants out. No b over 2 pi ln L plus A over L. Oh my god. Then I get I wire, the I wire dt. I wire. Oh, okay. Now I see it. Here you have to use the integration trick. So you have to note that actually d I wire squared over dt equals to 2 times I wire as d I wire times dt. So actually this guy, right, is half d I wire squared dt integrate from what? Remember, we have to use the correct limits here. I wire originally is 0. It's I naught and then to 0. But again, I don't care about sign. I want positive. And I naught squared, guys, because your differential is I wire squared. So this should be I naught squared. Okay. So this is just half I naught squared. Oh, and then we can finally write. E equals to mu. Oh my god. Okay, this is quite crazy. U naught squared b squared. Okay, I don't want to simplify it already lah, but you all get the idea. Okay, next. Uh, why is the limit I naught squared? I got a question. So the limit is I naught squared, right? Is because this is this is what you're integrating through the time. And this is basically d I wire squared, right? So at time t equals to 0, well, my I wire squared equals to 0. And at time t equals to, sorry, at time t equals to 0, my I wire squared equals to I naught squared. This, this is your differential, right? So this is your differential at that particular time. It's like a, oh, why I naught? I naught because they said is I naught originally. They said the current through the wire is I naught originally. Makes sense? Oh, are you asking me you should flip the limits of integration? Okay, yeah, you get it. Yeah, can. Okay, nice. Thankfully, I could live solve that one. Next, what two? Let's do 210. EMI. Oh, it's USA4. Okay. Eh, but USA4, you all have the solutions, right? Y'all can just, y'all can just find it lah. But wait, I'll see if this one has like good. It's a good question. Wait, this one, right? Oh yeah, B, wait, D and E. Wow. Uh, wow, it looks very long. I don't know if. Okay, you know what? I think I'll skip this question because you all can find the solution online also, and because there's some other questions that's in the problem set also. Yeah. Okay, let's go through 2.12. SPhO. I think some of y'all may have done this. So again, is we use a superconducting, the trick of a superconductor, right? Basically, uh, there's a shell A, radius, length L. It initially has uniform current flowing with a certain magnitude. It's basically a solenoid. Then there's also another solenoid B, and a certain mass, certain radius, certain length. It initially has no current flowing through it, and both of them are superconductor. Positioned infinitely far away from shell A, so my magnetic flux is actually 0 originally, and it's a lot of move. It's launched with initial velocity v, axis of symmetry line, limit of velocity v such that it will fill the length of the space. So basically, it means that, yeah, it's something like this. So first of all, okay, let's look at what happens, right? I know that the flux is conserved. What happens when I move this guy closer to A? What happens when I move B closer to A? Well, okay, let's say that my I is actually like that. My flux, this is my flux, right? So now this guy will have A will cause some flux through here, right? Due to A. This is due to A. But then this guy B will oppose. So this is the opposing flux. So that means there'll be a current like this. I prime. Let's call this I prime. Now, when this guy has a current like this, uh, then there's some more flux coming through here, right? But then A now says I want to oppose this new flux because A is a superconductor also. So the magnetic flux through A must be conserved. So it wants to oppose. Then how does it oppose this new flux? Well, it creates like that, something like this. This opposing flux. So it adds more current. Let's call this I prime prime. Okay. So so this is the added the current right. Yeah. So what happens in the end? Well, let's look at a cross section first. I know that uh I know that there'll be some I prime, and I know that this the big guy will be flowing in the opposite direction. This is I prime prime, right? So uh so first of all, let's think of what I must impose, right? I know that the B field inside a solenoid, right, is an I, right? And then you know that the B field inside here must be zero, right? So you know what? Let's call this whole current call this guy I2, right? So my B field inside here must be zero, and that means that I prime has to be equal to I2, right? Does this make sense? Because this guy will create a B field pointing inside, I2 will create a B field pointing out. No, it doesn't make sense. Okay. The original magnetic flux through the small superconductor was zero. Hence, the final magnetic flux through the small superconductor must be zero. These are the final currents through the small and big superconductor. It must be the case that the magnetic flux through this guy must be zero. Oh yeah, you got it. Yeah, because the magnetic field inside the solenoid is proportional to I, then it must be the case that I prime equals to I2. So you can cancel out inside this guy. Okay, that's my first equation. But then how is this related to the original I? How are both quantities related to the original I? Then we need to use the second equation, which is that the magnetic flux through the big guy through A is also conserved. So the original magnetic flux I, okay, the original magnetic flux is proportional to, because the turns per unit length, let me see, uh because these are like identical shells lah, right? So the magnetic flux will be proportional to I times A lah, right? So uh let's consider the positive direction to be the direction that points out, right? So by equating both magnetic fluxes, right? Wait, I will ignore all the constants first. So I'll say that the SPhO equals to what? Equals to I multiplied by IR squared. I'll ignore constants. The constants are all the same. Okay, you shouldn't do this in your exam, but I'll ignore it for now. Then sine u is what? Sine u is I2 times pi r squared. This I2 will cause a uniform field outside. But then what? This I prime actually opposes. I prime will oppose, right? So it should be a minus I prime. And then look, but the area is only, because your solenoid, your effective area is only here. The B will only be here. Outside, I don't care. It's B equals 0 for ideal solenoid. So this will be pi I over 2 squared. Okay. I, 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 I equate this. Okay. And then after that, I can find my uh, I can find my I2 and I in terms of I. Well, I'll just check the official solutions real quick so I know I'm going in the right direction. I haven't made any mistakes so far. Yeah. In the end, you'll get I prime equals to 4 over 3I. Yeah. Then now how you find V leh? Then you should already have some intuition because they give you M, they give you V. So you already think it's KE, right? So maybe it's the energy approach. And then how what what relates inductors to energy? Then you immediately think this guy, this guy, right? So it's just a conservation of energy thing. So the initial energy, which is UB d tau initial equals to UB d tau final. And this is different. This is different because you have to consider because the magnetic field here is zero, but then the magnetic field here is only by I2, is 4/3 of the B original, right? And then you have to integrate d tau f and then plus sorry, this one plus half mv squared. And you equate and then you solve for V. Someone asked, aren't both superconductors? No, 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 no. So the person asked, both regions should be zero because A is a superconductor too. But no, A, right, there was originally, wait, let's see. It originally has a certain magnitude I already. So originally it has some magnetic flux through it already. This magnetic flux is conserved. Yeah. So that's how we solve for that's how we get this equation. This equation is the conservation of magnetic flux in A. And this equation is the conservation of magnetic flux in B. So two equations for both. And then our final energy conservation, that solve the equation altogether. Okay. Um, 2.14. Okay. Let's see. I don't think I can live solve this one. So okay, so two infinitely long charged thin walled cylinders, radii R1 and R2 are located in a vacuum. They give you mass and charge per unit length, m and plus minus q. You can rotate freely about the axis. Find the electric field strength from the axis. They give away Gauss law, so it's just uh yeah, what's what? The it's basically it's like a line charge, so first one. Oh, sorry, HPQ. Yeah, because it's per unit length. Yeah. E ER when the cylinders rotate in the same direction. Um. Okay, so because these are like uniformly charged and they are thin-walled cylinders, so it's basically a solenoid. It's a solenoid, right? Um. And you know that now you want to find you know that B of a solenoid is mu naught times your turns per unit length times I, right? But actually, you can generalize this. B equals to mu naught K, where K is the surface current density, which is your current per uh, perpendicular length. Okay. So meaning like, for example, if like 300 ampere here, and then here's like 10 meter, because it's the length is the current comes here, then the length is perpendicular to the current. So then your K is just 300 over 10, right? Um, and from how this one goes to this one, quite straightforward, right? Because your N, because for each like each piercing line, right, it is like it contributes to the current lah. So the total number of current is the N times the individual current, and then you're just dividing by the perpendicular length. So you'll get K, right? So B equals to mu naught K, and then now you just need to find K of uh of the cylinder lah. So what is K? K is current per length. So, and then what is current? Okay, because you only have charge, you have rotating charge. So you your current is actually the amount of charge that passes through a unit time, right? So what is so suppose that uh there's some length L here, okay, and there's some angle d theta, okay. So in time dt, okay, as the relevant charge here is q l. My pen is so terrible. Okay, the relevant charge is ql. Will pass through, right? So will pass through this area, pass through this area, right? So now my charge over time, okay, is is this guy. But then how do I relate it with omega? Because my omega is d theta over dt. Oh wait, I'm sorry. So the charge is not q. It's like it's this tiny fragment of this whole circle, right? So actually should be q over d theta, right? Sorry, let me. So this should be q over d theta over dt because there's this tiny fragment of charge, right? Then we want to find this. So let me just see, right? And then okay, something's a bit wrong. QL passes through this area. Uh, okay, sorry. Okay, so this should be Q times d theta over 2 pi. Yeah, d theta 2 pi over 2 pi is the angular like amount of charge here, right? So okay, what I'm saying is that in time dt, right, this amount of charge that I've shaded will pass through this region. So basically, I'm finding the charge over the time at which to find the current, right? Wait, Jaden. Actually no. Kai, do you understand what's happening, or is it like, are you a bit confused? Okay. Wait, this is not good. Wait, some people are saying they are confused. Okay, so okay, let's put it like this. Imagine I have a imagine I have a ring of charge. Imagine I have a ring of charge. Okay, this is charge density lambda. It rotates around at angular speed omega. Find the current. Okay. So what I'm going to say is that current is charge over time. It is a charge that passes through a certain point per unit time. Let's call this point A. Okay. Let's consider all the charges here. Okay. These charges stand an angle d theta. And let's suppose that after time dt, all of these charges will have passed point A. Are you all still with me? So now my question is, what is the charge? Well, the total charge is your lambda, your charge density, multiplied by your dl. And dl is omega theta. No, sorry. dl is r d theta. Okay, so this is radius r. So this is the amount of charge. This is the amount of charge that passes through point A uh, in time dt. Okay. So your current is charge per time. D theta over dt is omega. Hence your current is lambda r omega. Now we basically have a cylinder, right? And what I'm saying is that this guy has is rotating like that, and it has it and it has a charge per unit length of q, right? And we're trying to find the current density. Okay, we're trying to find the current density, which is the current per length. Meaning, okay, if guys, I know it's 10. I think once we finish part B, we'll be done. Okay, because Hao Yang will send the solutions to you all. Okay, but I want to get this concept right because it's really important. So I'll just go through. I'll finish part B and then we'll be done. So we want to find the current per length. Meaning, given okay, I cut this thing and I say, given a length L, what's the current? What's the current going through? So because this cylinder is rotating like that, right? Now I know that there'll be charges going into the page. So there's definitely a current. I just want to find the current. That's all. Okay. So what is this current? Okay. So the current is a charge that passes through per unit time. Okay. So what I want to do now is that I want to bring this to a 2D. 2D, so it's just like that. Because we have symmetry anyways, so we can do this. Okay, 2D top view. Say now this is point A. This is point A. And then say in time dt, right? This amount of charge will pass through A. So it'll look something like this after time dt. So this is the amount of charge that passes through A, right? After time dt. What is this amount of charge? Well, okay, it's your charge density, charge per unit length, multiplied by L, which is the length here, right? Wait. So, okay, but wow, how to explain this? Okay, it's not the charge density. Uh, Q is your charge per length L, meaning it's like this whole across this whole circle. But we are only considering a section e theta of the circle that has angular span e theta over 2 pi. So the charge we are considering, okay, is d theta over 2 pi of the total charge. Agree. Hence, the charge density that we are considering is d theta over 2 pi of the total charge density. So it should be Q as d theta over 2 pi. Okay. So this is charge density. Then I multiply, right, uh, d theta over 2 pi. Then I divide by dt. So this is the amount of charge that flows through. This is your dt. This q omega over 2 pi. Then after that, your to find your B is just a solenoid lah. So this is your K, and then B is mu naught K. Yeah, I think okay. I think I'll stop here. Um, if y'all still don't get this, you can try to visualize it in 2 dimensions. You can also do it Griffiths. Griffiths has a section about current density. It's really important, so you can look through that. Yeah. I think I'll stop here in view of the time. Do you have any like final questions about the topic? Any questions or like questions about like anything like can be like iPhone, sport, or anything? Oh, okay. If not, I hope you all enjoy the lesson. If I can, like just get your, I'll stop streaming. But I just want to show you all something real quick. So this is quite exciting. Okay, so if y'all have Instagrams, right, you can check you can check this thing out. Okay, let me just share screen. So this is Founders Forge. It is my latest passion project. We are a community of over 20 national and international level student founders. So our passion projects, we grew them from nothing, and we believe really strongly in sharing them, sharing how to build your own passion projects, your own ground up initiatives with different secondary schools around Singapore. So we're currently partnering with 5 to 6 secondary schools already, representing to like thousands of students actually next year, already like confirmed. Currently we are releasing posts like we haven't released any posts yet, but they're coming soon. So y'all can follow and just check it out. I just promote right? It's quite exciting. If y'all enjoy the lesson, so yeah, I mean that's all. Okay, y'all can Leroy, can they can go now, right? Or anything else to do?
Yeah, can go lah. Yeah.
Yeah, I hope you all enjoy the lesson. Bye guys.
Nothing.
Thank you.
Thank you.
Thanks.
Bye bye. Thanks, guys.